Welcome back to The Explainer. If you're managing enterprise IT or building out high-throughput blockchain networks, you already know the post-quantum shift is giving engineers a massive operational headache right now. Look, the mathematics to protect our networks from future quantum computers, those have already been standardized. But actually putting those standards into production is causing severe real-world friction. Today, we're going to explore a really fascinating unified architecture called KLTu. It was engineered from the ground up to solve these exact deployment nightmares, and it's pretty incredible how it works.
Okay, let's dive into this. We're going to roadmap our journey today, from the current severe network frictions we're dealing with, straight through to a highly efficient, unified cryptographic future using KLTu's 16-bit solution. We'll look at how it shrinks signature bloat, check out the hard benchmarking data on speed and energy, dive into side-channel security, and finally look at what this all means for the future.
So, part one. Let's break down the post-quantum friction.
Here is the reality we face right now. Mathematically correct NIST standards are fundamentally breaking our high-throughput environments, and it all comes down to a core algebraic fracture in the math. Think about ML-KEM, which is the standard for key encapsulation. It's built perfectly on a 16-bit prime modulus, where the value Q equals 3,329. But then you look at ML-DSA, or Dilithium, the standard for digital signatures. That one is built on a massive 23-bit prime modulus, where Q equals over 8.3 million. This mismatch literally forces your systems to maintain entirely separate, completely redundant arithmetic pipelines just to function.
So what does this algebraic fracture actually mean out in the wild? Well, it's pretty brutal. Because of this modulus mismatch, ML-DSA signatures blow up and completely blow past the standard 1500-byte Ethernet limit. We're talking MTU fragmentation, IP layer delays, the whole 9 yards. It's like trying to shove a giant freight truck down a one-lane alleyway. For blockchain developers, this bloated payload inflates your cal data costs and drives up orphan block rates. Plus, you've got multi-core scaling failing to amortize static uncore power, leaving you with a huge energy drain. And honestly, worst of all, Dilithium's 23-bit math completely blocks seamless integration with fully homomorphic encryption, which strictly relies on 16-bit math. Add in some residual side-channel timing leaks, and you've got a massive, massive bottleneck on your hands.
Which brings us to part 2. KLTu's 16-bit solution. To fix these exact bottlenecks, we obviously need an elegant engineering solution. Enter Kinetic Lattice Topology, or KLTu for short. This is a unified post-quantum engine. What it does is it actually consolidates key encapsulation, digital signatures, and homomorphic encryption all over a single shared 16-bit ring kernel. That's right, absolutely everything operates on that exact same Q equals 3,329 mathematical foundation. By putting everything under one roof, it solves the friction by completely eliminating the need for those disjoint heterogeneous pipelines. And this brilliantly illustrates how secure this unified approach really is. When you run the lattice hardness head-to-head, KEM 16 is bit exact to the ML-KEM standard. We're talking a literal 0.00 difference in classical lattice cost. And for the signatures, DSA 16 diverges slightly by design to use that 16-bit ring, but it still retains incredibly robust secret key recovery margins. We are talking margins exceeding 214 bits at level 3 and 286 bits at level 5. That safely and easily exceeds all commercial requirements. All right, part 3, shrinking the signature bloat.
Let's talk about the most immediate, real-world network benefit of getting everything onto this unified 16-bit math. Remember that network fragmentation we just talked about? Well, the reference ML-DSA 65 signature comes in at a really heavy 3,309 bytes. That practically guarantees your network is going to fragment packets. But the DSA 16 level 3 signature was deliberately engineered to fix this operational nightmare and fit securely inside standard network payload limits. So the big question is, just how small did they manage to get it?
Down to just 1,043 bytes. Seriously, that's it. By mapping the signature to the 16-bit ring, the DSA 16 level 3 signature shrinks dramatically. This is a total game changer because it means both your public key and the signature sit perfectly inside a single 1,500-byte Ethernet MTU frame. Boom. Packet drops? Eliminated. Retransmission overhead? Gone. It makes things incredibly efficient across latency-critical financial and blockchain networks.
Let's move on to part 4, benchmarking speed and energy.
So, we've solved the payload bloat, but how fast is this 16-bit core when you actually spin it up? So, the crucial point is clearly visible right here in the verification latencies. Doing the math on a smaller 16-bit modulus yields incredible speed. Look at level 3.
KL2's DSA-16 verification takes a median of just 17.40 microseconds. That is 3.68 times faster than the baseline reference library. And at level 5, it hits 23.41 microseconds, making it a staggering 4.27 times faster.
When we start looking at concurrent workloads, the throughput scaling is just fantastic. KEM-16 reliably dominates the ML-KEM reference library across 1 to 4 threads. It safely supports those high-frequency cryptographic loads without stalling out at all, constantly pulling from its dedicated entropy substrate with 0 dropouts. But honestly, the DSA-16 plane is where the throughput gains are truly jaw-dropping. Notice how perfectly the throughput scales linearly here. By the time you hit 4 threads, DSA-16 verification reaches an incredible 278,946 operations per second. That is almost 4 times higher than liboq. That radically, fundamentally expands the platform capacity for enterprise infrastructures.
And of course, doing operations faster means you're burning way less energy. Because KL2 runs with such massive operational density, it actually amortizes the static, uncore power of your server package. Check this out. At 4 threads, KL2's energy per operation drops all the way down to just 0.438 millijoules. That is an energy reduction of over 3.2 times compared to the baseline. And for anyone running a data center, you know that translates directly into significantly lower operating costs.
Next up, Part 5, Side-Channel Security Triumphs. Now, beyond raw speed and packet size, if you're operating in multi-tenant cloud environments, your cryptographic implementations absolutely have to defend against microarchitectural timing leaks right at the hardware level. The absolute gold standard to prove an algorithm doesn't leak secret keys through microtiming variations is the Industrial Test Vector Leakage Assessment, or TVLA. And the pass threshold for this is incredibly strict. Your t-value has to be less than 4.5 across 20,000 interleaved executions. It is a massive hurdle to clear.
Now, what's really interesting about this slide is the stark visual contrast. You can clearly see the dark fail boxes for the reference ML-DSA verifications. They actually fail the industrial TVLA gate because of timing variability within Dilithium's hint reconstruction paths. But then you look at the clean, light-colored pass boxes for KL2's DSA-16. Because KL2 enforces a constant working set pipeline, DSA-16 just sails right through these stringent side-channel assessments seamlessly.
Finally, Part 6, the unified cryptographic future. Let's pull all these threads together. We've seen how standardizing on this 16-bit ring drops your packet sizes and saves you a ton of power. But standardizing on this ring also perfectly sets up your infrastructure for the future. You see, the 16-bit ring natively matches leveled, fully homomorphic encryption schemes like BGV, BFV, and CKKS, meaning you're ready to compute on encrypted data without needing some redundant, clunky math stack. Plus, KL2 gives you 0 overhead switching. You get to run the highly efficient DSA-16 for all your high-speed internals, and then use policy-driven FIPS 204 cosigning to bridge flawlessly to standard regulatory compliance right at your external network boundaries. You literally get the best of both worlds.
So I want to leave you with this provocative thought. As AI continues to drive this completely unprecedented demand for confidential encrypted analytics, how will your infrastructure actually handle the post-quantum shift without getting crushed under the weight of dual pipeline costs? It's a critical question and something you definitely need to evaluate for your own system's roadmap. Thanks so much for joining me on this explainer, and stay curious.